Thanks, James. So yeah, thanks everybody. And this is Youming. I'm dialing in from Sydney, Australia. So it's now okay. Yes, I write 29th of May here, but actually here now is 30th of May. So the date is a little bit different from the Sydney viewpoint. Yes. First, this is Youming, and thanks for the organizers and of course you sitting here for this opportunity. And we'll explore some interesting connections between tensors and graphs, hopefully interesting. And there will be 2 lectures because it was deputy group and now it's teams. So that's why it's only 2. I really hope that I can get 3, but then it's the 3rd one will be on Saturday, which is outside my work schedule. So anyway, we'll have 2, and hopefully it will be less fatigue at the end of the 2nd lecture. And some of the materials will be used for tensor isomorphism. I was hoping that you would have seen the tensor isomorphism by now, but then I checked the schedule that it seems that the tensor isomorphism stuff will go after my lecture. So I will also introduce what tensor isomorphism is and so on. But I will introduce from the very naive computer science viewpoint. So there will be pictures and so on. Not, probably not in the style of the next 2 lecturers, Pete and Josh McLeod. So yeah, some of the materials hopefully will be useful for tensor isomorphism. And for example, if Xiaorui Sun is going to give a talk next week, there will be some connections with his work on tensor isomorphism and group pattern. So yeah, that's some opening line, and if there's anything unclear, just let me know. And yeah, let's get started. So tensors and graphs, maybe there will be some unexpected match observed in the past few years. For example, when you talk about tensors, right? Actually for me, tensors are like just cuboids of numbers or cubes of numbers. So this is what I think when I think of tensors, it will be often of this format. So it's just a cube and a few numbers within in it. So it's also called sometimes called multi-way arrays, hypermatrices, and of course it's recording multilinear algebraic structure. And in the morning, probably you'll see where it's a connection with determinant varieties. That's more like algebraic geometry, and also bilinear map. That's more algebra. So that's probably some of the items you will think about when you talk about tensors. On the other hand, if you look at graphs, right? Here is a very naive graph, 5 vertices and 5 edges. So when we talk about graphs, we always think about, for example, there are objects, right? The vertices are objects, and we are trying to record their relation. And of course, graphs are a prime object in combinatorics, mostly. And when we talk about graphs, we can also think of like networks. And for mathematical problems, you may have heard of graph coloring, like the four-color theorem and so on. For graphs, if you look at some like modern graph textbook, you will see that many questions about graphs are of this flavor, namely extremal or the probabilistic questions. So that's tensors and graphs, and they are some of the items you will think about when we talk about these objects. So you may find it interesting to see that there are actually some very interesting connections between these 2 types of objects. So now we are going to talk about these matrices of linear forms, and this is where we are going to see graphs and tensors meet. So hopefully in the morning from Christopher's lecture, you've seen the so-called matrices of linear form, right? So for example, this is a 2x2 matrix with linear forms in 3 variables, x1, x2, and x3. And so this is just an example of matrices of linear form. And you probably also say that this is just one way to encode like 3 tensors, or tensors in the 3 directions or 3-way arrays. So these are matrices of linear forms. It's just one convenient way to write tensors on 2-dimensional papers. And then, if you start from a graph, we can actually build some special matrices of linear forms. So, and these constructions, they start from, they were first discovered and used by TAGA and Lomas, so who are like one of the few main contributors to the creation of graph theory. And this construction is also quite naive. For example, if you look at this is a bipartite graph, right? So you see that this graph has 4 vertices and partitioned into 2 parts, the orange part and the blue part. And the edges will only go between the orange part and the blue part. So I will label the vertices of the orange part by, say, 1, 2, 3, 4. And the vertices on the blue part by 1 prime, 2 prime, and so on, just to distinguish between left and right parts. And then you see that there are 3 edges. From this graph, you can actually build such a matrix. You can see that this is just a matrix of linear forms. And because there is one edge between 1 and 1 prime, so you put the variable x11, it's just a name for convenience. You put the variable x11 at the 1 and 1 prime position. And similarly, there's an edge between 1, 2 prime, so you put a variable x12 here. There's an edge between 2, 1 prime, you put x21 here. And because there is no edge between 2 and 2 prime, so you put 0 here. So this is a pretty naive construction that how you basically you put in a fresh variable or 0 depending on whether there is an edge in the corresponding position or not. So this is from bipartite graph to special matrix of linear forms. So this is, but on the other hand, you know that there are some graphs that you cannot have a bipartition like this. For example, this is the general graph. This is a general, undirected, and simple graph. So this will be when we talk about general graphs, it will be of this form. So then you see that it has it's just a triangle. And for general graphs, if you want to do such a construction, it will be a little bit complicated. Now, you are going to construct it for 3 by 3. Now this is a 3 vertex graph. You are going to construct a 3 by 3 matrix, but now this matrix will be skew symmetric. Namely, xij equals the inverse of xij equals the inverse of xji. And I probably made some mistakes, so yeah. Yeah, it will be easier to write like this. 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3. Okay? So you see that the point here is that if there is an edge between 1 and 2, then you put at the 1, 2 position, you put x1, 2. Then in the 2, 1 position, you put the minus x1, 2, and so on. Of course, because now this is fully connected, so you have a full skew symmetric matrix of the linear forms. But if you remove this edge, for example, then you are going to put 0. You are going to put 0 in the corresponding position. Okay. So this is just from general graph to a matrix of linear forms. And the point here is that we're going to get some skew symmetric matrices. Okay. So now we see that we are going to see the formal recipe. These are just some examples. And you're going to see that the matrices of linear form we constructed from graphs are special, because for bipartite graph, we say that every variable appears in, of course, at most one position. For example, here you use x11 in the 1, prime position. So you are not going to use x11 in other position, right? Because each time when there is an edge, you introduce a new fresh variable. And on the other hand, if you have undirected and simple graph, then each variable will appear in two positions, and the position will be just 1, 2 position and 2, 1 position, and it will appear in this relation. Namely, if x12 appears here, then the minus of x12 appears on the other position. So this is the construction from graphs to matrix of linear forms, and the matrices of linear forms, they just correspond to tensors. We will see some pictures later. Okay, so I hope this is clear for now. If there's any question, just let me know. Okay, so these 2 pages. So I will just quickly go over what we just covered. It's just writing what I said for these examples in the more formal terms. So I will use this bracket n to be the set of integers from 1 to n, and I will use bracket of n prime to be the set of integers 1 prime, 2 prime, and n prime. But this prime is mostly to use to distinguish between left and right parts of bipartite graph. And then I will have a set of variables x11, x12 up to xn, and we are going to say what is the bipartite graph here. A bipartite graph consists of the vertex set and the edge set. And the vertex set will be labeled, will be partitioned into 2 parts. The left part, for example, the vertices on the left part are indexed from 1 to up to n. The vertices on the right part will be indexed from 1 prime, 2 prime up to n prime. So this is the bipartite graph. And then this is the vertex set of bipartite graph. And the edge set will be simply a subset of the Cartesian product of the set n and the set n prime. So this is what we talk about when we talk about bipartite graphs in this lecture. So the point is that the vertex set are already labeled as such, and the edge set is just a subset of the Cartesian product of 2 sets. Okay? And then, starting from this graph G, we are going to construct a matrix of linear forms M G. And you can see that at the ij position, the entry at the ij position will be simply either with just a variable xij, if ij prime is an edge, and 0 otherwise, right? So this is just repeating what we were saying about this example. Just put it into the general format. So we quickly do one example here. So for example, this is a bipartite graph with 3 vertices on the left, 2 vertices on the right, and we are going to put the variables and zeros on this matrix. For example, 1, 1 prime, because there is an edge, you write x11. And for 1, 2 prime, you see that there is an edge, so you put x12. And for 2, 1 prime, then you put x21 because there is an edge between 2 and 1 prime. And but for 2, 2 prime, you say there is no edge, right? So you put 0 here. You put 0 here. And then for 3, 1 prime, because there is no edge, so you put 0 here. And then for 3, 2 prime, because there is this edge, so you put here. Sorry, actually 3, 2. Okay, so this is just what you do to construct a tensor or a matrix of linear forms starting from bipartite graph. And then similarly, for for general graphs, you can also have this such a procedure, right? And the point here is that it will be a little bit different. The point here is that the variable set will be xij, where I is less than j, because you are only going to use the unchoose2 variables, right? So it will be I less than j, so that's the difference from the bipartite setting. And when we talk about the so-called general simple undirected graph, we'll be talking about a graph with vertex set labeled by 1, 2, 3 up to n already. And then the edge set will be a subset of n choose 2, which is simply, this is simply the set of subsets of size 2 of size 2 subsets of the set 1, 2, 3 up to n. Okay. So this is the simple undirected graph. The edge set is simply just a subset of n choose 2. And the recipe here is that then we're going to construct the skew symmetry matrix MG. And the recipe that if you have for the ij position, you are going to put xij if ij is in the edge set and 0 otherwise. On the other hand, for ji position, you are going to put minus xij if ij is in E and 0 otherwise. So this is simply just repeating what we were doing for the triangle case, put it into the more general format. And we quickly do one example of this here. So first, you see that because it's skew symmetric, so the diagonal will be all 0. And then we just need to do the upper triangular case. For 1, 2, there is an edge, so it's x1, 2. For 1, 3, there is no edge. Then for 1, 4, there is an edge, 1, 4. And for 2, 3, there exists an edge. For 2, 4, there exists an edge. For 3, 4, no edge, 3, 2, 0. Then by skew symmetry, you know what the lower triangle will look like, right? So,
Mark, can you unmute and ask him why it has to be skew symmetric instead of symmetric?
We have a question.
yeah.
We have a question here. Why is this? I'll type it.
Sorry, I only hear why is this. Sorry, there's an echo here. What's the last bit of the question? Why is skew symmetric but not symmetric? Yes, actually you can also consider symmetric, and it will be useful in some setting. In this setting, skew symmetric will be useful because you will see. So it's also related to Farthing and so on. So I probably should have said that. Actually, there's a quiz about this. But it's useful for some context, for some graph theoretic context. So skew symmetry will be useful for you will see later. Okay, so yes, so now we have seen the connection between graphs and matrices, right? Between tensors. So now what we have done is that we have transformed graphs to tensors. Of course, the first question is why bother to do that, right? And then let's go back to Tata and Lomas. And this is they propose to you this thing, so there must be some reason. And so when Tata and Lomas come to this connection between graphs and tensors, they were thinking about graph matchings. So what is a graph matching? A graph matching is a set of disjoint edges. Namely, these edges, they do not share common vertices. For example, if you look at this graph, this is a bipartite graph, right? So you have the left side, right side, and you have 1, 2, 3, 4 edges. Then you can see that these two edges, this red one and this red one, they form a matching. They form a matching because they do not share vertices, right? On the other hand, if you choose these two edges, then it will not be a matching because they share this common vertex. So a matching in a graph is just a set of disjoint edges, which is quite easy to understand. But it's a pretty fundamental object in the study of graph theory, and Lombard actually has a monograph that's called graph matching or something for this topic. So for graph matchings, there are you can ask different types of questions for graph matchings. For example, you can ask the so-called structural questions. You can also ask the algorithmic questions about the so-called perfect and maximum matching. So a perfect matching is a matching that touches every vertex. So this is the meaning of perfect. And the maximum matching means that the size of the matching is the maximum among all matching. For example, if you look at this graph, you see that these red edges, they give a matching of size 2, right? They give a matching of size 2, but they are not perfect because they didn't touch these two edges, didn't touch this vertex and this vertex. On the other hand, you can simply find another matching, right? You can simply find another matching that touches, because it's a very small graph. You can find another matching that touches each vertex. Namely, if you don't use this one, if you don't use this edge, if you don't use this edge, but instead you use these two edges, right? Now you have found a perfect matching because now these three red edges, they touch every vertex and they don't share edges. They don't share vertices, so they form a matching and they touch every vertex, so it's a perfect matching. So this is an example of perfect matching. And sometimes, of course, for some graphs, like this graph, you will not be able to get a perfect matching. I think for this graph, if I'm not mistaken, the maximum matching size will be 2. For example, you can find these two edges. They form a matching of size 2, but you will not be able to find a matching of size 3. So in the 1940s, TAGA is considering how to characterize graphs without perfect matchings, like this type of graph. Okay. This is where he came across this construction of general graphs to skew symmetric matrices of the linear forms. And then in the 1970s, Lombard has been was pondering about how to efficiently decide if a graph has a perfect matching. And then he also observed that this tensor construction actually would be useful. So we will see that very soon. Okay. So yeah, turns out that this tensor viewpoint is helpful for TAGA and Lombard to consider the structural and the algorithmic questions about tensor. Okay, so we will see. Let's look at this. Let's look at the Lombard, what Lombard did. So basically, he came up with the so-called algebraic algorithm for graph perfect matching. And for convenience, we are going to illustrate this case for the bipartite case. Okay. So I'm just copying what we did, the recipe. This is just a recipe. And because now we are mostly concerned with perfect matchings, this is a recipe for bipartite graphs. And because we are mostly concerned with perfect matching now, so we only consider when the left part and the right part, they have the same size, right? Otherwise, you cannot get a perfect matching for the bipartite graph case. So this is just the same construction. The point is that if there is this edge in ij in E, then we are going to put in the matrix of linear form Mg with xij and 0 otherwise. So for example, this is the example we have been talking about from the very beginning. So this is just repeating the construction. And now we are going to see the first connection between graphs and tensors. So the observation for low Bazan part, definitely this is just an observation, is if the graph G has a perfect matching, right? This is a question about graphs. And the observation is that if and only if the determinant of MG is not the zero polynomial. Okay. So you see then you see that on this side, it's a question about tensors. So this is the first connection we see here between graph theoretic structures, perfect matching, and the tensor theoretic structure. Namely, that you take a linear form, matrix of linear form, you take its determinant, and you ask whether it's a zero polynomial or not. So this is the observation, and which leads to the connection. Okay. So I put this proof here. Okay, I put this proof here, but this is the observation, so you can probably imagine that it's not really difficult. And the key point is that for perfect matching, if you have a perfect matching, every perfect matching essentially corresponds to a permutation of a bipartite graph case. For example, if you have a perfect matching here, right? Then this just means that you have a permutation sending 1 to 2 and sending 2 to 1. In this simple case, of course, this is very easy to observe. In the general case, it's also not hard to see. So perfect matching in a bipartite graph corresponds to a permutation. On the other hand, if you expand the determinant of x, if you expand determinant of x, where x just equals xij, and now you have a full variable matrix. If you expand that, of course, by definition, you know that each monomial in the determinant expansion is of this format. So it also corresponds to a perfect permutation. So in other words, perfect matching on graph corresponds to permutations. Monomial Z determinant corresponds to permutations, and from this correspondence, you can easily see that this should be true. Okay, so I'll leave. I will send out the slides later, so you can read into this later, but this is essentially the idea. Okay. So, once we are given this connection between perfect matchings and determinant, then to test whether a graph has a perfect matching or not, translates to test whether the determinant of MG, which is a polynomial, right? Which is a polynomial in the variables xij, whether this is the zero polynomial or not. So now the question is, of course, how to test if determinant of MG is identically zero as a polynomial or not. Of course, but now the funny thing is that MG is a matrix of linear forms, so you cannot really do Gaussian elimination and so on from the algorithmic viewpoint. You can also not examine every monomial to see whether it appears to be determinant or not, because then that will be too slow. It takes n factorial time. So now the trick. So you cannot do this in this brute force way, but here is the trick. So the trick is that these xij's, they are variables, right? These xij, they are variables, so it means that you can substitute these xij with some concrete values. And in this case, it turns out if you substitute each variable xij with some value aij, and the aij is randomly sampled from the range from 1 to up to 2n. After substituting xij, you get the resulting matrix will not be a matrix of variables, right? It will be a matrix of numbers. Sorry, it should be scalar. It should be a resulting matrix of numbers. So once you get a matrix of numbers, then you can use whatever Gaussian elimination to compute the determinant value, right? And this can be done in polynomial time. So, yeah. So the resulting. So the idea is that now you randomly substitute Xij with Aij and compute the determinant of the resulting matrix. If your graph has no perfect matching, then of course the determinant of Ag will be always 0 because it's a 0 polynomial, right? It's a 0 polynomial, so whatever value you substitute into Xij, you get 0. But on the other hand, if your graph does have a perfect matching, which corresponds to the case that the determinant of Mg is not identical to 0, then there is a lemma called Schwarz-Lico lemma, which ensures that when you do this random substitution, then the determinant of Ag, which is the resulting matrix of numbers, is not 0. The probability will be larger or equal to 1/2. Okay, so that's the point. If you no perfect matching, identical to 0, you always get 0 value. If your graph has a perfect matching, determinant is not 0, then with at least some reasonable good probability, you will get that the determinant of Ag is not 0. So that's the distinction between the has perfect matching case and has no perfect matching case. And this gives you a pretty easy randomized algorithm to decide if a bipartite graph has perfect matching or not. Okay, so we have been mostly looking at the bipartite case, and in the general graph case, as you see that here, in the general graph case, we'll be dealing with skew symmetric matrices of linear form, right? So there was a very good question about why is skew symmetric but not symmetric. And this is where the skew symmetry is kicking in to be useful. And for general graph G, it turns out that we can also have an observation like that, like in the bipartite case. Bipartite case, we will use determinants. And for general graph G, you can also have the observation that the G has a perfect matching if and only if something about Mg. So you need to some polynomial about Mg is not the 0 polynomial. So from what I read about Christopher's lectures, you probably have seen this function or this polynomial. So I'm also accidentally just leashed it out. So essentially here we are talking about far things. Okay. So mainly the observation here is that for general graph to have a perfect matching, if and only if the far thing of Mg is not the 0 polynomial. Okay, and then the rest will go through. So what we have been talking about in the bipartite case about the algorithm and the random substituting values and getting an algorithm and so on. We will go through actually. So the rest will go through, and the only difference between the bipartite and the general case will be that you change from determinant to farthing. And if you expand this is also observation, because if you expand the farthing by its definition, then you will see that each term corresponds to a perfect matching. And here you can also see why skew symmetry is useful, because if a graph has an odd number of vertices, then the farthing will always be 0, right? So this is where the parity comes in. So for farthing, there is a parity issue. Okay, so this is just a hint on the algebraic algorithm for general graph perfect matching. Anything unclear? Okay, so yes. Okay, so now because I know that many of at least I heard from things that many of you are, very good and ambitious students. So let me just now pose this point. So we have seen a randomized efficient algorithm for graph perfect matching, right? And the outline of the algorithm is pretty simple, namely, you build a matrix of linear forms, and then for the variables, you substitute variables with random values, and then you compute the determinant or the function. So that's to test whether it's real or not. Use some sort of lemma to ensure that you have a distinction of the probabilities between the yes and no case. And we also see that the matrices of linear forms from graphs, they are actually pretty special, right? For bipartite graphs, it's special because every variable appears in at most one position. For undirected and simple graphs, each variable will appear in at most two positions. Now, if you want to go from this special matrices of linear form to general matrices of linear form, namely we don't restrict on the number of appearances of variables and so on. And then can you test if the determinant of a general matrix of linear forms is identically zero or not? Right? So this is an observation which actually goes back to Edmonds. Actually, the same randomized algorithm still applies. Right? If you think about the algorithm to test whether the determinant of MG is identical to zero or not, essentially there we are not using any special thing about these special structures. So the same randomized algorithm will still apply, namely you just substitute variables with random values, and once you get a matrix of numbers, then you compute the determinant of function. So that's easy, even for the general case. So this is the same randomized algorithm still applies, but can one devise a deterministic efficient algorithm for this? That's a very big question. Okay. So what do we know about testing if the determinant of general matrices of linear forms is identical to zero or not? And first we go back to graph setting, right? In the graph setting, we know that by Edmonds and the Hungarian method and so on. So we have known that for graph perfect matchings, bipartite or general, there exists deterministic efficient algorithms. So graph matching can be done in deterministic polynomial time. However, if you look at this general question, currently we don't know of any deterministic efficient algorithm. And it's a celebrated result by Cabanas and Pagliazzo in the early 2000s. They show that if you can devise a deterministic efficient algorithm for testing whether the determinant of general matrices of linear form is zero or not, actually it will imply something very significant in complexity theory. It's roughly, I'm putting quotes here, so take it with a grain of salt. It roughly implies that the algebraic P is not equal to algebraic NP. Okay, so this is a significant thing, right? So P versus NP is like one of the very fundamental basic open problem in computer science, theoretical computer science mathematics. And in order to achieve that, all you need to do is to devise a deterministic efficient algorithm to test whether the determinant of general matrices of linear form is identical to zero. Okay. So yeah, I hope that you can keep this problem in mind and think about it from time to time. Yeah, this is also, this type of work actually follows from another thing called hardness versus randomness principle, which a lot of celebrated theoretical computer scientists have contributed to. Okay, so now we are going to move away from perfect mappings to tensor isomorphism. Before that, any question? Okay, so now So we're going to, summarize a little bit. It has been like 45 minutes. That's a lecture already, but hopefully we will see 10,000 of them at least. So just to summarize a little bit, we have seen a recipe from graphs to make it of linear forms and beautiful tensors or three tensors. We have also seen a correspondence between perfect matchings and the non-zero determinants. Right? And in this lecture, we are going to see two more correspondences. The first one is about isomorphism testing or isomorphisms, and the graph iso and the tensor iso. The last one will be about independent sets and the so-called totally isotropic spaces. So depending on the time, probably we will not have time for this, but I will send out the slides and you can take a look at it later. But definitely we will have like 10-15 minutes to talk about these two, the connections between these two notions. And I also want to briefly mention that from the computational complexity viewpoint, the choice of these three questions from graphs are not actually quite random. So here we want to talk about, we have seen perfect matchings. We will talk about graph iso soon, and we have seen independent, we will talk about independent sets if we have time. So you probably also know that this is a very classical thing now in computational complexity. We have this NP, we have this understanding of P and P and so on. So we have problems that are in P, and they can be done indeterminately at one point in time. We also know like thousands or tens of thousands of NP complete problems. And there's a very classical theorem in complexity saying that if you believe P and NP are different, then between NP complete and P, there exists also the so-called NP indeterminate problems. Namely, these problems are not NP and they are not NP complete. And perfect matching, as we were saying, because of Edmonds algorithm and so on, so it's in P. And the independent set is like one of the few problems you need, NP complete problems. If you start from satisfiability, then you quickly go to independent set. So independent set is NP complete. And the graph iso is another, on the other hand, is a famous problem for being a candidate of NP intermediate problem. Maybe at some point, graph iso will be put in P, but so far, that's what we know. So you see that these three problems, they occupy different positions from the computational complexity viewpoint. And all these correspondences, they also have some interpretation in the computational complexity viewpoint because by the connections between these three pairs of notions, for example, for independent set, we actually, by the connection, it reduces to the so-called total isotropic spaces. And we will also see that graph iso essentially reduces to tensor iso. And the perfect matching reduces to testing whether the determinant of a matrix of linear forms is at 0 or not. So these correspondences, in other words, these correspondences also give us something in the computational complexity section. Okay, so graph iso and tensor iso. So graph iso, basically you are given two graphs. You want to know whether they are the same up to relabeling the vertices. For example, these are two graphs, right? And one graph, they look somewhat different because this is a cycle and this is a star. So they look different. But if you relabel the vertices, if you relabel the vertices of the second graph by doing 1, 2, 3, 4, 5, then you see that it's essentially a 5 cycle. Just put it in this way. So it's a 5 cycle because now we go from 1, 2, 2, 3, 3, 4, 4 times F1, right? So this is essentially just going through in this order. So in other words, these two graphs, they look differently, but you are able to relabel the vertex of the other one graph so that then these two graphs become exactly the same. So this is the graph isomorphism problem. And tensor iso. So yeah, I was browsing through the schedule, just realized that not sure whether you have seen tensor iso or not. So, but now I'm going to give you a very intuitive definition. So for now, okay, we'll be mostly talking about 3 tensors. So 3 tensors are just cubes of numbers, right? These are cubes of numbers, and we want to know whether these 3 tensors, they are the same up to basis changes of the 3 directions. Because you have 3 directions, so you can do linear combination this direction. Namely, you have the horizontal slices, you do linear combinations of the horizontal slices. Similarly, you have the vertical slices, you do linear combination of the vertical slices. And finally, you have the frontal slices, and you do linear combination of the frontal slices. After this, invertible changes, you want to know whether invertible changes, basis changes, you want to know whether these 2 cubes of numbers become exactly the same. So, yeah, this is just, briefly summarizing what I just said. You want to know whether there exists invertible matrix L, invertible matrix R, and the invertible matrix T, such that when you use L to do the linear combination of the horizontal slices, and you use the invertible matrix R to do linear combination of the vertical slices, and you use the invertible matrix T to do the linear combinations of the frontal slices, then you make B to be the same as A. Okay, so this is the tensor isomorphism problem. Now, of course, it explained intuitively. Okay, and of course, here is a formal definition. You can definitely write it in a formal definition. Namely, if you write your tensor A as a matrix tuple, such that this is essentially the frontal slices, right? You slice your, for example, you slice your matrix B according to the 3rd direction, then you will get a tuple of matrices. So if you have 2 tensors, A and B, now written in a matrix tuple format, and then the question is whether there exists n by n invertible matrices L, R, T, such that when you multiply L on the left, R on the right, then use T to do the linear combinations of these slices, then you make these 2 tuples of matrices to be the same. So that's the formal definition. Well, it is formal from the computer scientist viewpoint. Okay. So we also recorded it, right? We have the recipe going from graphs to matrix of linear forms. We have seen that. And the matrix of linear forms, of course, is just another way to record a 3 tensor. For example, we just use this very small example. We start with this bipartite graph. We construct this matrix of linear forms. And this matrix of linear forms, of course, depending on the variables, right? For x11, because x11, in this case, x11 only appears in one position, so it corresponds to this matrix. Then x12 appears in the 1-2 position and no others. So x12 gives you this matrix, and x21 gives you this matrix, right? So a matrix of linear forms, if you are collecting the coefficients of these variables, you get these matrices, and then you can collect these matrices as a tensor, right? Here, because you have 3 2x2 matrices, you will get 2x2x3 tensor. So yes, so that's the connection between graphs and tensors. Similarly, the suppose now you have two graphs, right? So for first graph, you start from the graph G, construct this 3-tensor TG. For the second graph H, you construct the 3-tensor TH. And now we are going to see the connection, right? We have two graphs. We want to know whether they are isomorphic or not. Then we build out these 3 tensors. And of course, for tensors, we also have this notion of tensor isomorphism. And of course, now the proposition, as you probably can expect, is that the two graphs are isomorphic as graphs, if and only if the two tensors are isomorphic as tensors. Okay? Yeah, so this is from this paper. Okay. So this is the main proposition. Namely, when you do this recipe from graphs to tensors, and you follow this recipe for two graphs, and you get two tensors, it turns out two graphs are isomorphic, if and only if the two tensors are isomorphic. So if you really think about it, it's actually it's kind of also an observation, It's not difficult. Here is essentially just an outline, just to illustrate some brief opening to if you want to go for the proof. But I assume that if you do it by yourself, probably you can do it. So I'll skip this proof outline. I'll share the slides later so you can have a look. Okay. But essentially here is the connection. Okay, two bipartite graphs are isomorphic if and only if the resulting tensors are isomorphic. So this proposition, it's simple, but it has some interesting implications. For example, it gives the reduction from graph iso to tensor iso, which means that from the worst case algorithm viewpoint, tensor iso cannot be too easy, because graph iso is not very easy from the worst case viewpoint. So and it also implies that if you can give a polynomial time argument for tensor iso, you also give a polynomial time argument for graph iso. So, but graph iso in P is still very difficult, so we don't know. This proposition was stated, for the bipartite case. But for the general case, you also have, for the general case, you will get something like fused metric matrices of linear form. And I just want to mention that the analogous result for general graphs actually also holds. So it's another paper. It's this one, I don't know, this one is a little bit tricky, this one is pretty straightforward. This proof is a little bit tricky, so I'm still trying to figure out why it's tricky in this case, but at least it should be true. And the third implication of such a proposition is that it may hint that at some point we may try to borrow techniques from graph iso to, tackle tensor iso. For example, such as the so-called individualization and refinement, graphs with figure lemon. So these are very, classical arguments for graph iso, because graph iso have been very intensive studied since the 1960s and 1950s. So there's a vast literature on graph iso. So once we have this connection in mind, maybe we can try to borrow, or at least think about borrowing techniques from graph iso to tensor iso. So yes, so I'm coming to the last 2 minutes. So sorry, this I hope that is not too long for you, especially for you lecture. The last one is about the independent sets and the so-called total isotropic space. You can say that here basically I introduce what independent sets are, what total isotropic spaces are. They're both very classical. And you can also have some connection like this, namely, you still go from the general graph G to the skew symmetric matrix of linear form MG. And the proposition is that the max size of independent sets in G is equal to the max dimension of total isotropic spaces in MG. So you also have such a connection in terms of the max size or max dimension. Okay. So I'll share the slides later so you can see the definitions of these two notions. And now we come to the last minute. So, okay. So the summary is pretty, I hope that the message of this lecture is clear. That is, we have some very simple recipes of constructing tensors from graphs. And we have seen the three correspondences of structures. On the graph side, we have seen perfect matchings at most of them, independent sets. Well, we haven't really go through this, but it's easy actually. For the tensor side, the perfect matching will correspond to non-zero determinants. For the isomorphism setting, you also have tensor isomorphism. And for the correspondence of independent sets will be the so-called totally isotropic spaces. So we have seen some correspondences of this structure. Just as a spoiler alert, and James, Pete, you guys know much better than me that you can extend these correspondences between graphs and tensors to groups. Okay? So yeah, this one I'm not exactly sure, but as algorithm is pretty clear. You can start from graphs, build tensors, and then you can start from tensors and build groups. James will give you the construction if you're asking. And you also have correspondences of isomorphic notions of graphs, tensors, and groups. Similarly, for independent sets, so if you go to groups, and the correspondence between total isotropic spaces in the group set will be a billion subgroups. Okay, so of course, certain are billion subgroups, but this is in other words, you can extend these correspondences via a tensor and go from graphs to groups. So this is just to spoiler alert about the further correspondence. And in the next lecture, we will see that these correspondences not just give you correspondences between the structures, but also about the questions and techniques. So we are aiming towards a more interesting questions and the techniques. So that will be the lecture tomorrow. Okay, thanks so much. That's all for what I want to talk about today. Thank you.
Since we're having audio problems, if you can ask a question that can be typed, it's great. Otherwise, we will follow up by email or something. It'd be hard to do it verbally, is all I'm saying.
Questions will be typed.
Yes, probably, there seems to be some echo.
The group correspondence at the end is for all groups or just for class 2 P groups?
Yes, that's a very good question. So far for this correspondence, let me just go to the chat. Yeah, this correspondence is, for now, is mostly for class 2 groups, class 2P group. That's the skew symmetric setting. And also, if you just look at the bipartite graph, then it corresponds to general tensor, and then you can construct the so-called Brahana group from general tensor. And of course, upgain is responsible for all this. But on the other hand, I also want to add that some questions, when you talk about, for example, maximum and billion subgroups, namely, if you translate the question to groups, then the correspondence now is class 2P groups. But for some questions, you can ask with a general perspective about general groups, right? Like nice rank of a billion subgroups, general groups. So the questions, can be asked for general groups. But the correspondence here, yes, you are right. So far, it's mostly about the class 2P groups, exponent P groups. or resolve for unknown groups.
Let's try something.
Yes.
I'll mute him and then see if we can ask, because Christopher, you had a question. So try it now. Let's go, you can go ahead and ask now verbally. No feedback.
I'll try without feedback. Youming, you told us at length why we should care about the vanishing or non-vanishing of the path here. Yeah, and I understand that this has a correspondence in the graph flow that you wrote up. Are there similar graph theoretical reasons why I should care about the vanishing of the other minor ideals? Not just the vanishing of the path here?
Yeah, that's a very good question. So I don't quite know, but I think it's a very nice leading question. Maybe there are also like correspondences, some graph theory correspondences about the vanishing of the ideas of minors and so on. So, but yeah, I haven't really thought about it. So yeah, that's a very good question for sure.
Any other questions? All right, let's thank Youming.
Yeah, by the way, I'll share the slides, and if there are any questions,
Sorry, apologies.
There's no my email address and so on. So.
Okay. Bye, Youming. Okay.
Thanks, James.